quisiéramos agradecer al CEO por la invitación. Me dijo el doctor en la mañana que quería que la plática en inglés. Yo no tengo ningún inconveniente en darle en inglés. De hecho, me siento, por cuestiones técnicas, es más fácil en ocasiones darla en inglés porque todos los tecnicismos los aprendí en inglés, entonces para mí es más fácil, ¿no? Realmente. Pero si tienen alguna pregunta y no se sienten cómodos, la pueden hacer en español, no hay ningún problema, ¿no? La idea aquí es también, si ustedes van a dar una plática a un congreso internacional, pues lo tienen que dar en inglés y les van a escuchar en inglés también, pues qué mejor que de una vez, ¿no? Empiecen a practicar en esto. Sin más, este es el título. 2-6 Materials and Devices for Flexible Electronics and Radiation Sensors. I'm a professor of material science at the University of Texas in Dallas, obviously. A couple of people have been there with us already. My talk is divided in several things, okay? I will talk probably a couple of minutes on our group because it's the people that actually does the work that I will show. Hopefully, I will convince you that flexible electronics is indeed a very exciting field, and that although people think that organic has to be used or has to be the materials of choice for flexible electronics, we have already developed a few inorganic materials that can be used in flexible electronics application. And I will show you, in particular, cadmium sulfide, a case study, I call it, because you will see how we take this material from just the concept to understand the material itself, how to do the synthesis of material, how to understand the defects in the materials, to make the device, to make a sensor. So the whole 9 yards in there. And within this case study, I'll show you the effect of doping, how we control doping on cadmium sulfide. I will also show you some work that we're doing in oxide-based, so we're doing both 2,6 and oxide-based materials for flexible electronics. Then you will see that for both of these materials, we use really expensive tools, PVD, E-beam, tools that are very expensive, not only to buy, but also to maintain and to operate. So what we do is that once we develop the understanding of the material, what we do next is we transfer to large area sort of compatible tools or techniques. And among the techniques that we use, it's chemical bath deposition. A few people here should be looking into this. We have also a media printer to do the printing of the materials. We do micro drop casting, and we also do transfer methods. Okay, so we're going to look at some of those. And towards the end, I will show you a prototype that we have developed for neutron detectors. So to get to this prototype demonstration, we had to understand everything. Okay, so we need to understand fundamentals in terms of doping of the material. We need to understand also how to make it large. And also we need to understand devices, because it's not just a sensor, it's not just the sensor. The sensor has a circuitry to control the sensor. It has energy storage, a battery. It has power management. So we have to put all those things together. And then if we need to communicate that sensor with the computer, we need to have a computer scientist that can help us to write the code to communicate with the computer. Okay? So all these things we put it together to do this prototype demonstration. This is my group there at UT Dallas. A lot of people actually do the work. You will see a lot of people from Mexico. Beto is from Sonora. Rodolfo is also from Sonora. Marta is from Coahuila. Marcela is from Coahuila also. Marta is actually from Colombia. And we have a lot of visiting scholars. Okay, so people that are in program in Mexico, that they go and visit us there. They stay for up to 1 year or so. And they do learn a lot. So there are a lot of opportunities for this. This is where our lab is located. This is the building is called the Natural Science and Engineering Research Laboratory. We have a clean room here, and I will show you I will show you a little bit more about the clean room in the next slide. Our department is the 3rd and 4th floor. Okay, so material science. In the 2nd floor we have chemists, physicists, and in the 1st floor we have biologists. And in the basement, we have a lot of animals for research that people do. They're mostly mice and rabbits. This is the clean room where we do a lot of the research that I will show you here. We have 5 bays, we call it, so 5 sections. The first section is a diffusion. In this diffusion section, we do a lot of thermal treatments. We grow silicon oxide, silicon nitride. We can dope silicon as well. We have the thin film deposition. And there we have sputtering systems, we have E-beam deposition system, And we also have, you may not see towards the end in there, we have etching systems. So we can deposit films, but we can also selectively remove some of those films as well. This is probably the most important part of the clean room. This is the photolithography area. In this photolithography area, we have this tool in there. It's a mask writer. So if I want to do a device, I need to have a mask. And to have the mask, I need to have a mask writer. That's an expensive tool. This is like $2 million. Not a lot of universities can afford that. So we're lucky we have that one. And what is nice about having these kind of tools is that I can have an idea about a device on paper, and then we can go and write that mask in the mask writer, and then they can start making the device. Okay, probably within a couple of days you can start actually fabricating devices. We have surface preparation for regular wet etching of the material we deposit. Inside the clean room we also have a characterization bay. So if for some reason I deposit the film, and I suspect that the film may be thicker than the thickness that I was trying to deposit, I simply go without leaving the clean room. So these are the bays that I'm showing there. The door there is the access to the characterization bay. So I can take the film to the SEM to look at the thickness or to look at the roughness. We have also spectroscopic ellipsometry to look at thickness. If the film is a dielectric, for instance. So you don't have to go out of the clean room to measure some of the characteristics of the film, which is great because if you exit the clean room, then the film becomes contaminated. You cannot move it back in the clean room. So this is a good thing to have the characterization in there. So let's move on now to flexible electronics. Okay, so hopefully you know where we make all these devices, and you will relieve some of the data that I will be showing you. So if we say flexible electronics, we're very familiar with silicon, right? So you have a computer, you have a cell phone, you have silicon in your pocket probably, okay? Can we use silicon for flexible electronics? And the answer is maybe, and more likely not, okay? Why? The cost. Okay, the cost is very high for silicon. Okay, remember we're talking about large area here. This is the evolution of the wafer size for silicon. This is a 300 millimeter wafer size. This is a 200 millimeter. This is 150. So we have, for each one of these sizes, there is a need to build a manufacturing facility. The manufacturing facility for 300 millimeter tool is about $4,000 million. Okay, so $4 billion, very expensive. Not a lot of companies can afford that. Number one. Number two, even if you can afford that, this is not flexible, right? So if I put it in a flexible substrate, it will not bend. People can thin down the silicon to make it flexible, but that process is very expensive as well, so it keeps increasing the cost. So silicon, in my opinion, is not a good solution for flexible. Now, it might be a good solution for a part of the flexible substrate or the flexible device. If I have a flexible screen, okay, that needs a little piece of silicon here to control the, let's say, chip register, to move the screen, well, it's okay because I still can fold the screen, and this little tiny piece of silicon will fold with the screen. But most of the screen has to be on a flexible substrate with another different material. So silicon may have some application that will not necessarily be the main material for flexible electronics. The application that we're looking at are something like this, okay? So we all think of flexible displays like this. So imagine the architects that work on the field, instead of having this thick binder with sort of the blueprints, they can have a single sort of display like this where they can look at the blueprint. We all are always waiting for the flexible cell phone. This is quite interesting. This is a tattoo, right? So it's a tattoo that is not permanent, so you can remove it. Now this tattoo can look at the glucose levels on people with diabetes. Okay, so it goes into a person without going inside the body, so you can actually track the glucose levels in person. Okay, once this goes bad, simply remove it, put another one. So we cannot put a piece of silicone in there, right? Because otherwise you couldn't move your arm. So it has to be flexible. So that's what I'm talking about here. Hopefully, you know, flexible photovoltaics, flexible samples. So there are many applications there. You know, the imagination is basically the only limitation. There are a couple of non-conventional fabrication ways to do these flexible electronics. One is, don't care about the substrate. We can use a rigid substrate, then I fabricate a flexible device on top, then I remove the rigid substrate, and I have my devices sort of freestanding. Okay. The next thing is I will have this glued into a plastic. Now I have a way to transfer and to move this. The cost is high because we're wasting a substrate every time. The other way is we can build the substrates or the flexible devices directly on top of the flexible substrate or plastic. What is the problem there? Well, the problem there is temperature. I cannot process at temperatures higher than 250 Celsius because if I put the plastic at 300, it's going to burn, right? So I'm limited by the temperature in this case. So in this case, I'm not limited by the temperature, but it's very high in cost. In this case, it's very inexpensive, but I'm limited by the temperature. That's why people is looking at organic-based material, because most of the organic-based material will be compatible with the different software that can be used on flexible electronics. Okay. Other potential application, and we are heavily working on this application. We call it the tunnel of truth, right? And we all go through airports, and every time you need to remove, especially in the emails, you need to remove the shoes, you need to remove the belt and everything, right? So our project is developing large area sensors for neutrons, for radioactive material, for gammas. We're also looking into infrared detectors, terahertz detectors. So the idea is to have a tunnel, okay, where people can simply, for those of you that have traveled in the airport that have the electronic stairs, so you go on the stand on the electronic stairs, then they move, right? While on top, you can have this tunnel, so you can monitor people without having them to take the luggage or clothes off to check. So we're looking into this sort of application. Why flexible electronics is relevant here? Because it's a large area, right? So we need to make this tunnel out of silicon. It's going to be very expensive. Number one. Number two, silicon is very sensitive to gamma, so when we have false positives. So there are a lot of things that hopefully I will convince you that our material is better. What can flexible electronics do? High-speed computing, right? So we will never be competing with Intel, okay? We will never have really high speed. We will not have RF application either, like cell phones. And why? Because if you look at it, this is outdated, but this is the mobility, which is how fast the cable moves in the material. This is for amorphous silicon. If you have a computer, your screen is actually made out of amorphous silicon. And you can see that the mobility for amorphous silicon is in the order of 1, okay? Compared with silicon in the Intel chip that is about 1300 or 1300. So it's 1300 higher. For most of the organics, the mobility is about 10. Okay, so it's very difficult to have an organic material that will do computing and operation at the rate that silicon achieves. So forget about flexible electronics with high-speed computer or computing with Intel. These are just a few more details in comparing silicon MOSFETs with organic thin transistors, and the materials that we are developing actually fall in between. Not as low mobility as organic thin transistors, not as high as the MOSFET, but number one, we can process all of these materials using low cost, large area compatible systems. Okay. The same as organics. The problem with organics is the mobility is very low. Number one. Number two, reliability might be an issue. Okay? Whereas in this case, reliability is not an issue. If we have computers made out of amorphous silicon or polycrystalline silicon, that's not an issue. When we go more into the details for the material itself, whenever we want to make a device, we need to have both type of carriers, N-type and P-type. Okay? For organic devices, there is already a good solution for P-type, which is a pentacene. It's very stable. Is not as unreliable as other materials. There is no clear sort of need for N-type, for electron transport for organic-based materials. There are some promising materials, but there is no clear solution yet. For inorganic semiconductors, there is a really good N-type, amorphous silicon, but there is no good P-type. So there is a challenge, and there is an opportunity there to develop P-type silicon or P-type inorganic thin film material. So this is the area that we are working on heavily. And some of the materials that we're working at is the chalcogenide. Okay, why the chalcogenide? Because chalcogenides, we have N and we have P as well. Okay, 1, 2. This is mobility. This is Hall effect mobility. Drift mobility is not field effect mobility, but the mobility is quite high. It's quite acceptable. Okay, both for N type as well as P type. That's just half of the equation here. The other thing is the electron or carrier concentration. So if we plot the electron or carrier concentration for a number of materials in there, obviously if it has more electrons than holes, it's going to be an N type. If it has more holes than electrons, it's a P type. What is interesting here is that zinc oxide is very difficult to make P type, and the reason is that the N type or the electron concentration is pretty high. We need to reduce the N concentration about 6 orders of magnitude, which is very difficult. But if we pick, for instance, this the CAC79, so this is an N type, but I only need to reduce the N or the electron concentration about 2 orders of magnitude to overcome with P now, so I can easily dope this material P and N, so I can have with the same material system N and P behavior, which is great for device performance. The strategy that we follow to do this is, first, we use expensive tools like sputtering, thermal evaporation, PCVD, and in particular in our lab, pulsed laser deposition. That allows to identify materials that will have high performance, but they are very expensive. But I don't need to worry about contamination. I don't need to worry about leftover from the organics or anything like that. Once we identify the conditions, what we do is we transfer these to cheap, inexpensive techniques, chemical body deposition, spin coating, we have the ninja printer as well, and roll to roll. Okay, these tools or these techniques are low cost, large area, and large throughput, very fast. But if you want to develop a material with the right doping using chemical body deposition, good luck. Okay, for those of you doing chemical body deposition, you will need to do hundreds and hundreds of experiments to just get the material to work, and then you need to worry about doping. But if I go and tell you, you need to do the cat sulfide, 100 nanometer stick, and you need to put 1% copper and anneal it at 400 Celsius, and that will give you a P-type, that's great, you know at least where to start. If you don't know that, first you need to understand how to grow the cat sulfide, what is the effect of the substrate, 2, what is the proper ratio of the different chemicals, 2, do I need to anneal it, if I need to start doping it, what is the proper concentration of doping, and which one is the right precursor for the doping. So it's very difficult to do sort of process development with these tools. So let's move on to post-laser deposition, and I won't even attempt to explain here, room full of experts on optics here, but basically what we have a laser, okay, and we have 5 or 6 different targets, okay, and what we do is we direct the laser to the target, which ablates the target and evaporates into the substrate. We can do a co-deposition of up to 6 different targets, which is great. That way we have target A, target B, and we can dope target A or substrate A with whatever I have in the target B. So it's great for sort of materials screening in there. So let's look at some of the data that we have from this PLD. So we have in this case, the resistivity. This is a cadmium sulfide film, okay? And I will spend a couple of minutes here because this is key to understand the rest of the talk. So we have resistivity, deposition pressure, and the PLD system, okay? You can see that at 20 millitorr, this is the deposition pressure. The resistivity is about 10 to the minus 1 ohm centimeter. As I increase the pressure from 20 to 80 millitorr, the resistivity increases by almost 5 orders of magnitude. So why is that? It's obviously never changing the microstructure, because if I look at the surface morphology, because if I look at this field by SEM, this is 20 millitorr, 40 millitorr, and 70 millitorr. So they're about the same. So morphology is not an issue. If I look at X-ray diffraction, 20 to 80 millitorr, there's basically no stress. This, we use it to explain this increase there, but I'm not going into that. So there is no change in the microstructure. There is no change in the surface morphology of the film. So what is going on? I mean, we're only simply changing the deposition pressure. It shouldn't matter, but it does. Then we go into electrical characterization. The electrical characterization tells us, remember that the conductivity of any material is given by the carrier concentration and the carrier mobility. Basically, how many carriers you have and how fast they move. Those two. we measure by Hall as function of the position pressure. This is the carrier mobility, remains about the same. It goes up from about 2 or 3 to about 10, but the carrier concentration actually drops more and more and more as we increase the deposition pressure. So obviously, what is causing this increase in resistivity is the decrease in carrier concentration. So we're actually reducing the carrier concentration in the film. We're making it more intrinsic. But now we know what is causing this resistivity change is the carrier concentration. But we don't know from the materials perspective what is causing this. So what we do next is RBS, Rutherford backscattering. So with Rutherford backscattering, what we have now is the deposition pressure here. You can see that whenever we are closing to 70, 80, or even 90 millimeter, the film becomes more stoichiometric. Okay? So what is causing this increase in carrier concentration here is simply the excess of cadmium. So we have cadmium interstitials and we have sulfur vacancies. So we have sulfur vacancies, cadmium interstitials that act as a donor for the cadmium sulfide, which increases the carrier concentration. So now we know that we have these vacancies, these interstitials. Since we know that that is happening, we can now play with the material to fix this. Okay, so that's how we do the material development. And what will be really great for us is to collaborate with the institute to find where the sulfur vacancies or the cadmium vacancies are located within the band gap of the material, or if we have other defects. And if you plot this assembly log scale, if you plot resistivity versus sulfur to cadmium ratios, almost a linear sort of relation ratio, which is clear that that's indeed what is happening. Once we understand all these concepts, all these things in the material, then we go and make devices. If you try to make the device without knowing the material, good luck. It's very, very difficult. Okay? So we do thin film transistors, and I just put this slide here to explain what we extract from thin film transistors. So in the thin film transistor, we have the source of the electrons or holes. We have the drain. This is an N-type. We have an insulator. We have a gate. If this is an N-type, what we simply do is we apply a positive voltage here, which polarizes the insulator, which generates, so this is positive, then the insulator, the interface with the gate in the insulator will be negative, and the interface with the semiconductor and the insulator will be positive, so it attracts that positive charge, attracts electrons here, which generates now a channel. So now I have a connection with the source and the drain, so now the transistor is on. And how that looks like? So basically I'm increasing the gate voltage here. Whenever I see the drain current increasing, that means that I'm accumulating the electrons in there. So my transistor is on. From this plot, I can extract carrier mobility and VT voltage. The VT is the threshold voltage, which is the voltage at which the transistor turns on. From the saturation current, I can extract the mobility. So we do a lot of these different characterization. Another way is to do this, what's called IDVD. These are called family of course. These are different type of measurement, but this is the most important measurement. And from there, we extract all this. We extract, like I said, field effect mobility, which is different than drift mobility. Subthreshold slope. The subthreshold slope here is how fast. So one thing is to know when the transistor turns on. The other is important thing to know is how fast the transistor turns on. Because I can have a transistor that turns on like this, right? So it's very slow. What I want is the subthreshold slope to be as high, as low as possible. On off, basically when the transistor is off, the transistor is on. There's a lot of information to extract from there, and we do this. So going back to our friend cat sulfide, okay? So this is a transistor that we fabricated. We have the gate, we have the gate electric, we have the semiconductor, and source that is exactly the same as I showed you in the previous slide. This is a function of pressure, okay? Same as I showed you 2 or 3 slides ago. So in the position pressure, you can see that as you go from higher pressure, from lower pressure to higher pressure, the transistor becomes better and better. Okay, so these are experimental plots or experimental results from the measurements of the transistor. The films that are more conductive, the 60 millitorr, the I off is higher than the others because it's more conductive. So it's more difficult to turn the transistor off. And then we extract all sorts of things like mobility, pressure, voltage as function of pressure. From there, we're preparing ourselves to make more complex devices. So transistor is simply the start of this. Then we go and dot these guys. what do we do to dope? We can dope it more, we can dope it P or we can dope it N, okay? And to do that, we start with an undoped cat sulfide with the lowest carrier concentration, okay? And then we simply add more or less copper or indium sulfide. The indium sulfide is to make it more N, the copper sulfide is to make it more P. So here we started with a carbon sulfide undoped with a carrier concentration of about 10 to the 16 or so. We can dope it more N, or we can dope it more P. So now we have N and P, and now we can start looking at making simple homojunction diodes, right? So we have not the best diode, but we have a rectification of about 2.5 orders of magnitude for a diode that is fully made in the clean rooms. Other materials that we look at are the oxides, okay? And I will skip this one, but basically, if we look at the indium gallium zinc oxide, this very interesting system. We have gallium oxide, we have indium oxide, we have zinc oxide. This is simply the thermal diagram for the microstructure, either amorphous or crystalline. So if you put a lot of indium oxide, it's going to be polycrystalline. If you put a lot of zinc oxide, it's going to be polycrystalline. Okay. Now, if we look at now the mobility, okay, if the highest mobility, the red, is whenever we put more indium oxide. The problem is that if I put a lot of indium oxide, my film is going to be polycrystalline. And that is bad because the definition for a grain boundary is a defect. Okay, so if I have a defect in the film, that's going to generate a lot of trapping in those grain boundaries. So ideally, we would like to have an amorphous material. So what we need to do is to somehow put a trade-off performance with stability. And no wonder most of the devices made out of indium gallium zinc oxide are actually almost 1:1, where it's not the greatest mobility, but it's an amorphous material. So these kind of studies are necessary to understand whenever you're trying to do devices. Then with the positive material by PLD, and we did exactly the same. So 10 millitorr all the way to 80 millitorr, since we understood from the cat sulfide. And this is XPS data. And what we have is, from the XPS data, we extracted the oxygen vacancy concentration as function of deposition pressure. Obviously, as we reduce the deposition pressure, the oxygen vacancy, the concentration of oxygen vacancy decreases, therefore the film becomes more resistive, okay? And I won't bother you with all the extra data we did, but basically, the next thing is, what is the maximum concentration of oxygen vacancy that we can have in this system so that we don't have a degenerated semiconductor. And the degenerated semiconductor is whenever the Fermi level is above the conduction band. Okay, so it doesn't behave as a semiconductor anymore. To extract that, we did a Hall effect measurement as function of temperature. This is 1/T, okay? So this, so what we have is that as we increase the temperature, you can see that the only film that has some thermally activated mobility is 17.5 millitorr. So we can tell that film is a semiconductor. The 10 or 15 is not a semiconductor because you don't have this thermally activated behavior whenever you plot mobility as function of 1/T. So that's the film that we need to use for devices. Okay. The next thing is we pick that film, we make devices, again, transistors as function of, in this case, thicknesses. So we can make transistor with indium gallium zinc oxide films as thin as 25 nanometers. Okay, so this is the process flow. This is the substrate. This is the electric. This is the semiconductor with it, and the source and drain with good mobilities as well. We also do zinc oxide. Okay, the same study for zinc oxide. All right. This is the transistor. Cross section. This is the top view of the transistor. This is the source, the drain, and the gate. And then we start making devices, more complex devices. This is a substrate, a plastic substrate with the UTD logo in the back. If you can see the logo, that means that we are successful and we can fabricate transparent devices. So we have a bunch of transistors here that you don't see because they are transparent. We made everything with transparent materials. The gate is transparent, the electric, semiconductor, source, and drain. We use aluminum doped zinc oxide, which is a conductive material and is transparent also. This that you see there are what we call alignment marks. When we need to make many masks, we need to align them. So the fact that you don't see the devices that means that are fully transparent, this is great. And just to make sure, we did the transmittance measurements. So we have about 80% or so transmittance with mobilities in the order of 10 or so centimeters squared per volt second, so which is really cool. But we're going to do more complex devices. We're going to do inverters. Inverters are really important for circuit fabrication, and I'll show you later why. So these are the inverters in there. These are some of the characteristics. So we get gains in the order of 150 or so for zinc oxide, and all of these are processed at temperature below 100 Celsius. So we have, gone from the materials to the cat sulfide to oxides to simple transistors to now more complex devices, and it keeps getting more and more complex. But before I go into the more complex devices, what I'll show you is how we do the transfer to large area. Okay, this is chemical bath deposition. It's a very simple process. As long as you have a beaker, a heater, and water, and the chemicals, we're good to go. Okay. So you have, for instance, for cadmium sulfide, we use cadmium chloride as a precursor. And we have thiourea, which is the sulfur precursor, which hydrolyzes by the pH, okay, and with the temperature as well. This is data for cat sulfide deposit by chemical bath deposition, solution-based process. This is different thicknesses, 30 all the way up to 150 nanometers. And what we plot is again the transistor mobility as function of thickness of the film. As we go thicker in the film, the mobility gets really good, about 20. Okay, but there is a clear correlation with the grain size. It's not necessarily the grain size, but as much as the cluster size. As we go thicker, you can see that if you compare 30 nanometers with 150, the 150 you can clearly see these clusters. Okay, so this larger cluster indicates that you have less defects in the film. If you have less number of defects in the film, your mobility is going to increase. Okay, so that's just simply showing that the transistor with chemical bath deposited cat sulfide works. Then with also transparent devices with cat sulfide. You make it very thin, the cat sulfide will be transparent. You can rarely see some yellowish in there in the corner. But there is a picture of the nephew of the student that was doing this experiment. So the devices are there. They are also unflexible. When we compare flexible or glass devices, they are about the same. Okay, so there is no intrinsic degradation of the devices whenever we put it on a flexible substrate. Remember that at the beginning of the talk I mentioned about the transfer process. We also do that, and that's very simple. Basically, what we have developed is this is the silicon surface, silicon wafer. Okay, so it's rigid substrate, and then we deposit by salt gel a germanium oxide film about 1 micron. Germanium oxide is soluble in water. Okay, that's why germanium never made it as opposite to silicon. And then we do the entire processing. We don't really care about temperature anymore because it's on silicon, right? Silicon we can process up to 1300, 1400 Celsius. We do the process. Once we finish doing the processing, what we do is we open holes here and then put it in water. The water goes in and dissolves the germanium, and then our flexible substrate or substrate kind of or devices float in the water, which is already covered by a paralleling layer. So what we have now is we simply rotate this. This is very thick, so I don't really need to transfer to another substrate. The paralleling itself is the substrate, and we have devices that are completely flexible now that we can use as the patch that I mentioned before, okay, or the tattoo that I mentioned before. Again, the mobility is much better. Remember before it was for zinc oxide like 10. Now we can get up to 20 or so, really good transistor characteristics. So we have this process as well. We also do inkjet process. Remember we're talking about large area. So we have what is called micro or micro drop casting. We have an ink that has the cadmium and the sulfur. Okay. The advantage of this is that I only use the material where I need it. In photolithography, you need to cover the entire substrate and then you remove selected areas. In this case, I have the ink made of cadmium and sulfur. I printed the substrate and then I heat it up because I need to provide energy to the reaction for the reaction to proceed. Once I form the film, I continue with the thin film fabrication. And we have some transistor built with this process. Not the best good-looking transistor, but at least they work. We call this the micro drop casting. Usually, I can send the presentation, but most of the information is there on the bottom of the slide. We also do typical inkjet printing, right? In this case, what we have is we print, for instance, the sulfur, and then we print the cadmium, and then sulfur and cadmium, and in that way we can also generate transistors. Again, not the best looking transistor, but at least we demonstrated that these devices work with inkjet process. The advantage of the inkjet process is not, believe it or not, is not doing this, it's actually creating the ink. Creating the ink is quite a bit of a problem. The good thing in our process here is that we don't have, most people does the ink process using nanoparticles. In our case, we don't use nanoparticles, we use the precursors itself. But if you have the nanoparticles in the ink, it's actually easier to make better devices. So let me show you how we put all these things together to make a prototype for radiation. Okay? And the detector that I will be showing you has a very simple concept. It's a very simple concept. We have a p-n junction diode, or we might have a p-n junction or an avalanche diode. We have, this is the metallurgical junction, so we have the p-type material, we have the n-type material. Now you understand why I'm very interested in N and P, because that will help me do this sensor. Then we generate what is called a depletion region. That depletion region is when the N and the P combine, and we have this depletion region. When the ionizing radiation passes through, it will generate electrons and holes that I can collect on either side of the detector. Okay, that's the concept. That is a very simple concept. The way that we're doing it is different in the sense that we have our substrate, these are our sensors here, and these are our circuits. Okay, so if we look at closely here, what we have in the substrate, then we have PIN sensors in the bottom. Then we have this boron 10, which is, I'll explain a little bit later, which is a converting layer for neutrons. We have avalanche photodiode, which is the sensor for photons coming from the scintillator. So if I have, let's look at the neutron first. If the neutron comes through, it will not interact with the scintillator. Okay, so it doesn't interact, but it will interact with boron 10. The cross section for neutrons for boron 10 is very huge. So the neutron interacts with boron 10, it generates a lithium 7 negatively charged, and it generates an alpha particle. An alpha particle is a helium 2+, so it's a positive charge. When the positive charge goes through my sensor here, it generates electron and hole pairs, which I collect. Okay, so now I'm detecting the neutrons. The advantage here is that I can collect neutrons coming from the front or from the back. If I'm looking at gamma detection, I need to have a scintillator, so the gamma will interact with the scintillator. It will generate a photon as a consequence of that interaction. That photon will interact with my avalanche photodiode, which will go and generate one electron and hole, which will be accelerated with the electric field, and will go through the avalanche process, and I can detect the gammas now. So this is the concept, right? So we can fabricate, I show you that we can fabricate the PIN diode, we can fabricate this, we can fabricate the avalanche photodiodes. We can simply use commercial plastic scintillators to do this kind of system. This is the concept that we were discussing yesterday. This whole concept we're using inorganic, but this big proposal was actually based on this idea. So what we propose is to use an organic-based material, a diode. This is my organic diode, and we say we're going to put nanoparticles of gadolinium-157 or boron 10, and then on top of this, we're going to put also more boron 10. So the neutron will come here. This is just a magnification of this area. So the neutron comes here, we interact with the boron 10, generate the same alphas, lithium, which will be detected by the diode. Or if it goes through, it might interact with the nanoparticle in the organic material. So this is something that we can, for the proposal, that we can certainly pursue with CEO here. Cost is the main driver for this. If I look at the cost, right now, telluride single crystal is used for a radiation detector, mostly for neutrons. $475 for 1 by 1 centimeter, right? About the size of my thumbnail. Silicon is about $250, okay? The telluride module, the solar module, costs about $72 per meter square, which, comparing with silicon, is about 72 cents as compared to $250 for silicon. Okay, so it's very inexpensive, and that's why people are really interested in this technology. So we have to do science before we go and build the device, right? So the science here is we run simulation, Monte Carlo simulation. This is the pulse with the signal. and this is the diode thickness. So this is the thickness of the diode that I'm going to use as the sensor. And what we did is we compare silicon with multiple materials. We will compare silicon with cat telluride. So if we look at white open symbols with blue, you can see that it's about the same as cat telluride is about the same as silicon. So there is no intrinsic benefit of using silicon as compared to cat telluride. So we can use simply cat telluride. So there is no benefit. The next thing is to look at the efficiency. How are we going to make this more efficient? The more efficient is we do the sensor here. This is cat sulfide. Then we put the 110, and we put another die on top. We call this the sandwich approach. Okay. And with the sandwich approach, we can get efficiencies in the order of 13%. If we don't put the sandwich approach, our efficiency is like 6% or no 7%. Okay, so ideally it should double, right, from 7 to 14. But there are some other factors in there that keeps that ratio. So the efficiency reaches about 13% or so, which is close now to a helium-3, which is what is used, a Geiger counter that is used for regular radiation detector. So this is putting the converting layer outside the diode. I can also put the converting material inside the diode. The problem then is that to get to 13% efficiency, so I need to have a diode that is as thick as 25 microns. Okay, so very thick diode, and that means that the diode is going to be, it will require to be run at really high voltage to have a really wide depletion width. So this might not be a good way to do it, but this has only 20% boron inside. So if we go to 40% boron, we'll go from 25 to about 12.5. But if I put more boron, I may create more defects in the diode. So this is actually data that we took from a Californium-252, a radioactive source neutron that we had at UT Dallas. So we have basically the diode, no conversion layer. We don't have any counts. Then we put only the diode on the top, we get about 95 counts. We put the diode in the bottom, we get 265 or 63 counts. Then we do the sandwich approach, and we get 470 counts. So it does help to have the sandwich approach, and this is with actual neutrons striking on the sensor. So it does prove that this system, this process works. But it's only half of the equation. We need to have the circuits also. And the circuits, we made it with zinc oxide. Okay? And this is the amplifier. This is called a 3-stage amplifier. So it's one stage, 2 stage, 3 stage. Here are the circuits, here are the diodes. This is the cross section. Okay? This is the Pullman version of what I was showing before. This is the diode here. And we have some of the circuits in there. So each pulse that you see here is every time that the neutron strikes. Okay, so the neutron strikes, it generates a pulse that we collect. Okay. Knowing all this, what we did next is the prototype. Okay, so we got students from computer science, electrical engineering, and a couple of guys from material science. So Sergey was in charge of the detection, basically fabricating the diode. Okay, and Christopher was in charge of the amplification stage. So take the signal out and make it or amplify it. Then we need to shape the signal so that we can read it, and the software, the communication. So we did this all the way from the diodes, the amplification, to an actual app on your iPhone or your iPad. So this is the sensor working, and what we have is, these are the sensors. This is the app that we made. Most of the room that you see there is from the batteries. He's going to put the radioactive alpha source close by. So whenever John put the alpha source in there, you can see that the counts go up. Okay, so every time that he puts so it's really counting the alphas striking on the diode, right, which is great, which is what we really were looking at. Then we got a little more fancier, and then we actually had to buy a little car. We put the alpha source in there, and then we made this tunnel. So assuming that the car was passing by a bridge, right, with our sensors. Okay, so the most difficult part was to control the car in there. But the car was sitting in there, you can see the counts. So the car goes, this is where we have the sensor. So the car passes by, we don't have any more counts, so it then moves it back, and it goes up again. So it is sensing It's not only so. Hopefully you get the whole picture, which is our sensors are with cat telluride, cat sulfide. The cat sulfide, we have to understand the doping and all those sort of things, right? And then how to make the device, and then how to make the circuits, and then how to make the whole concept, how to put the whole concept together to get to this kind of application. We have another. I don't have the. I couldn't find the video. We have another video, but we have now much larger sort of scheme for the detector. So with that, I'll finish my talk. I hopefully convince you there are multiple opportunities for flexible electronics, because we're basically developing a new device architecture. Okay, so silicon is great, but it's really mature, and we need something else. However, I don't think that, in my personal opinion, I don't think that performance is the primary goal for this. Performance will be secondary. Reliability will drive this technology. I always give this example, and I should have mentioned this at the beginning, but we work with a company in Arizona to develop a smart bandage, okay, a smart bandage. That thing was, whenever we finished, it was going to cost like $25, okay? So that was to look at whenever you get a wound, to see if it's infected, okay? So $25, but you can go to a store and buy 10 of these bandages for $1. So I was telling the guy, if I have the option, I'll buy 10 and simply look at if he's infected or not, and then throw it away and put another one, rather than having a band-aid that will tell me and send to my cell phone or whatever if my wound is infected. So that's not practical. However, if you have a wound inside your body, imagine that you had surgery, then you can put that sort of a band-aid inside, and that can send the information to your cell phone and then to your doctor if your surgery went wrong, or if after a couple of weeks you have infection, right? So in that case, it is practical. But in some other cases, it might not be practical. So in that case, application, like I mentioned, is what is going to drive this technology. There are multiple sort of applications that this technology can enable. I do believe that both the 2,6 and oxides are really promising to alternatives to organic-based devices. However, organic-based devices are also useful for other applications, especially in the bio area. This cat telluride thin film, cat telluride is the first time that is demonstrated. We're looking at gamma, we were demonstrating, we're looking at X-rays now. If we can enable all this, I think that reduce cost and the availability of industrial plants, like photovoltaic plants, will enable to further decrease the cost for this particular detector. So with that, I'll end my talk. Hopefully it was entertaining, and I'll be happy to answer any question that you might have. Thank you.
Is there any question?
Hi, congratulations. Nice. To be honest, I'm not too familiar with the flexible electronics, but I want to know what is the real status of this technology. I mean, how complex are the devices right now, and what is the next goal? What is the expectation of this technology?
Yeah, I don't think you can go and buy a flexible screen now, okay? So all new technology is normally implemented or introduced by stages, okay? Just to give you an example, the technology that you have in your cell phone now was developed 10 years ago, okay? So when I work at TI, we were developing the microprocessors that we're going to use in a cell phone in 2015, and I work in 2002, okay? So the flexible electronics technology now is at the stage where the concept has been demonstrated, okay? So now the technology has to be implemented in or by large companies like Samsung and LG. Now, one application that is out there is for the Kindle, the e-reader. The Kindle has a screen there that is made on a flexible stainless steel, okay? And the only reason for them to use this screen is because people used to drop the Kindle a lot and it will break on glass. But on stainless steel it doesn't break, okay? But it's not flexible, okay? So this is the first stage. So they're using a flexible substrate to fix a problem that doesn't really necessarily need a flexible substrate, but it needs the roughness basically the resistance of the substrate to fix a problem. So the next thing may be that Kindle takes it to a flexible device. So that's, for now, the only commercial application. There are multiple military applications. Okay, so the Army and a lot of the research in the flexible display center in Arizona is supported by the U.S. Department of Defense. They have screens here. I'm sure you guys are familiar with for the NFL the quarterbacks. They have these screens here. Okay, those are made that flexible because they get a lot of hits by the other players. So the U.S. Army also have these screens so they can transfer information back and forth without worrying about breaking it. So taking the long route here to answer, basically there are just a few commercial applications that you can use now. I think that we'll see far more coming in the next probably 5 years or so. Okay?
Any other questions?
What are the challenges about degradation of the organic material, and also what is the limit for currents, for current density? Because it is a soft material, it is a plastic, and probably heating is an issue.
Absolutely. So I think that the limitation for reliability is defined by where the device is going to be used. Okay, if it's going to be inside, it may be okay. If it's outside, it will need a much better encapsulation. For organic devices, whenever you finish the device, you need to encapsulate the device before you remove the device from the ambient where it was built. So you have a glove box with a nice environment, no oxygen, no moisture. You have to encapsulate it there before you take it out. Because as soon as you take it out, it's going to start degrading. So it has to be a lot on where it's going to be used. In terms of current, it's obviously a problem. The one thing is the thermal conductivity for organics is very low, right? So in most of the materials, at least the transistor will actually need to conduct current. Whenever you conduct current, you generate what is called the Joule heating. So you have the Joule heating, you have the organic semiconductor on the plastic, you have the Joule heating. There is no way to extract that heat out, so it will fail. So that's one thing. The good thing here is that those currents are normally very low, especially for organic light emitting diodes. The currents are very, 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 very low, in the order of micro amps or something like that. Very, very low. So it may not be as bad, but at some point it will degrade the material itself. So thermal conductivity is a problem also. That's why I'm doing inorganics now. I think it was another question there.
Concerning your detector, your neutron detector, very, very nice device. But I was wondering, well, two questions. One is, have you got any idea of the efficiency for, how many neutrons you have to put in to get one count? And the other one would be whether you have measured, I assume that you would have some degradation because you have this breaking of lithium and
Sure. Yeah, that's a very interesting question. So, yeah, for the first one, our benchmark is the helium-3, which is a Geiger counter. That guy has about 90% efficiency, okay? And it has 90% efficiency as long as your neutron hits the area, okay? Here is 0, right? So it has to hit here. So this, like I showed you, has about 13-14% efficiency. But if you cover a room as big as this with this chip technology, then the efficiency gets better, right? So if I have another slide there where I have like a helium-3 tube here, and you compare that with and I have a neutron source here, we run the simulation, versus having the same concept with the large area detector. So the efficiency is comparable once you make it large. Okay, so if my helium-3 is 90% efficiency and my system here is 16% or 13%, I need to make it like 6 times or so, or 7 times larger to have the same efficiency. So the short answer is about 13% is our efficiency, which is low compared with helium-3, but we can make it large to compensate for that. And the cost is about $100 versus $4,000 for the helium-3. And then you drop the helium-3 tube, then it breaks, right? 1 and 2, we're running out of helium-3, right? This project started because the Department of Defense said that by 2015 we were going to run out of helium-3 because they're not making any more nuclear weapons, right? And that's how they were generating helium-3 by the nuclear weapons. The other question, in terms of the degradation. So remember that we're looking here at thermal neutrons, okay? And we may have 2,000 thermal neutrons or so, okay? The thing there is that the thickness of the boron-10, I mean, if we look at the Avogadro's number, right, we will have like 6 times 10 to the 23rd or something atoms per mole. Now, I don't think we're going to run out of boron-10 because of the interaction. First, the device is going to fail. We have so many that we only need one, right? So we need one neutron with one boron-10 to generate an alpha particle in a lithium-7. We have not tested in a really high, intense radiation. So the plan is to do it at the INIM here in Toluca, right? But we haven't really tested a really high flux of neutron because we're looking at. So when people conceal these radioactive materials or weapons, they put lead, okay? And the lead will thermalize the neutron, but some thermal neutrons will make it out. So we're not actually looking at non-thermalized, we're looking at thermalized 25 milli-electron volts neutron. But yeah, I mean, that's a good thing to do, just test it on the high flux.
And how long did it take from the very beginning of your research to the final prototype?
Oh, for this?
Yeah.
Well, it depends how good the students are, right? It may take a year, it may take 50. No, I mean, these guys, they work very hard, right? So we started the neutron detector project in 2012, September. So about 2 years. But we have a lot of people also working, right? So, but the neat thing here is that, so we have experts on electrical engineering, computer science, and material science, chemistry, physics, and we all understand our role, and we need to coordinate our efforts, right, to a specific goal. So we all know what the goal is, and everybody works towards that goal. So we have, for instance, a guy that is looking at, very simple thing, right? So a guy that is looking at how to dope the cat sulfide. I mean, his PhD thesis is how to dope cat sulfide. And I have another guy whose PhD thesis is simply to look at closest space sublimation of other 2,6 materials, okay? And we have another guy whose thesis is simply look at the stability of zinc oxide. But we have another guy, one of the postdocs, whose job is to come up with the best diode using the data that the guy working with the cat sulfide and the cat telluride has, right? So he works with these two guys. So they might not see the whole picture, but each one has a specific contribution to the whole project. And that's why I think that it makes progress quite quickly, right? Because everybody works on their fundamental science to finish their PhD, but at the same time we have other team here that takes parts of this to make it to the clean room to make the device. All these devices were made at UTD, I mean in the clean room, in there. So having a clean room is really, really good because it allows you to do not only this, I mean you can do MEMS, you can do optoelectronic device, you can do a lot of things, right? So it's just basically limited by what you want to do.
Okay. Good. Manuel, thank you very much for the talk, and I give you later.
Thank you.